So thank you for the introduction. So I'm Alexis Morvan, and I'm a research scientist at Google. And today I'm going to talk about different circuit implementation we have used for the surface code and how we use this different circuit implementation to explore like the trade-off we have with our hardware. For this, things are not clicking where they are. Okay, so I will first go around like the standard implementation of the surface code and give back some result on this, and then I will present 3 different implementation of the surface code that offer different trade-off, and we will see how they trade-off fare. So let's first talk a bit about the standard implementation of the surface code. So everybody kind of like know about it a bit. There is like Z parity check, a tile of Z parity check and X parity check, and you need to implement a logical qubit on the grid square lattice of a square lattice of physical qubits like this, and the total number of qubits scale as 2d squared minus 1. So how does this work? The way this works is that you need to measure the parity on your data qubit using an ancilla qubit. I don't know if I can make this work. Okay, so you just, usually this is represented, like the syndrome extraction is represented as just having like 4C0 into an ancilla and then measuring. Here I'm showing like the syndrome extraction in like a small like time slice animation, just so you can see how the stabilizer evolved in time. To be fault tolerant, what you do is that two measurements of the repeated stabilizer measurement should agree. If they disagree, it means that there is an error that occurs in between. This can be captured with the notion of detecting region, and here I'm showing the detecting region. So you propagate the polyflow using this set of rules, and now this represents the Z sensitivity region in your circuit, meaning that if you have a non-commuting error inside this region, you will detect it into this detector. And here I'm showing like the time slice or the detector flow for this single detector. So this is what I'm saying. If you have like here a single X error here, it's going to get detected and it's going to trigger a detection event. Okay, of course, things are a bit more complex when you start to tile them. So now, if you look at inside of a regular surface code, like here, what you will see is that the detecting region span a lot of qubits. I think it's touched something like 9 qubits in total, instead of the 5 we showed right before, when you include all of the gates. And actually, it's also touched like a lot of C0. So the naive picture was showing we're touching like 8 C0, but in fact, if you look closely, you will see that in the full surface code, we are touching like 22 C0. So you are pretty sensible to a lot of error. So we find representing this detecting region with those dead slice extremely beneficial, because this helps you understand where the errors are coming from in a space-time frame. So here is a flattened out, non-animated detection fraction. So you always start from a single point, starting from an ancilla. Then you have an expansion phase of your detector. Then you end up at the end of the cycle where you do a measurement and you find back the usual stabilizer of the surface code, which is like a square. And then you have a contraction phase, putting the detector back into a single ancilla qubit that you can now measure. So now you need to tile this, and so this is showing like a tiling of X and Z at the same time. And of course, as soon as you have everybody at the same time, it starts to be a bit harder to read, but like figuring out a single detector is always useful. And it's going to be useful for us to see how we construct those alternatives to the surface code. Okay, so now I'm an experimentalist, and so what I want to know is how an implementation fare and how good is it. So to do this, what we do is memory experiments. So we prepare a logical state, Z or X logical +1 or -1, and we do a few cycles n time, and then we measure. So with this, we get detection probability like this here, and then we just repeat the same experiment for an increasing number of cycles, and we get an exponential increase of the logical error probability versus the number of cycles. This we fit and the fit gives us a logical error per cycle that is insensitive to the to the measurement and the preparation state. Of course, what we care is right now is that can we scale our device to larger distance in order to reach logical error rates that will allow application. To probe this, what we usually do is we measure the lambda. What is the lambda? Is the factor by which the logical error per cycle decrease when the code is increased by a distance of 2. So when you go from distance 3 to distance 5, you reduce by 1 lambda. When you go from distance 5 to distance 7, you reduce by 1 lambda, and so on and so forth. This is like the exponential reduction of error. But this also means that you need to increase the size or like the number of physical qubits that you need. But this is the quantity right now we are interested in, because this will tell us like what is the number of physical qubits we need in order to achieve the logical error rate we care. Okay, so this is the result from last year where we have shown first below threshold performance. So this is a comparison with our previous device, the Sycamore, where we barely reach the point where D3 and D5 were having the same error, and now we have a lambda of a factor 2, meaning that every distance we reduce the error rate by a factor 2, and this you can see between this curve here. So this is with the standard circuit implementation. No? So this was the circuit I want to show you, and so as we discussed, this architecture necessitates to have like a four neighbor per qubits architecture. And this is actually a hard constraint when you try to construct a device. And one of the ideas that was raised in this paper by Mike McQueen, Dave Bacon, and Craig Kidney was that you can actually relax some hardware constraint by implementing different time schedule for the gates. And here is the first example, which is using a 3-coupler schedule. And here I'm showing the animation of the dead slice. And so if you look closely, you will see that we start from the same point, and the first gate are the same, but at some point we change the gate pattern. And now the detector move a bit. And if you look even more closely, you will see that we are not using one of the direction for each qubit. This is maybe more apparent in a static picture. So this is the evolution of a single detector. You start from an ancilla qubit, you have this expansion cycle in one expansion phase in one cycle, where you go into the square that you are used to see, and then we have this contraction cycle. And if you look closely, you will see that we never use this direction in this pattern, because like the first layer and the last layer here are reusing the same direction. So this means in practice that you can design. Yes? So the dead slice is, so it's this, right, at each time. And this is going to be the representation of the detector. So those are the region where like, those are, so this is a circuit representation, right? And the blue represents like the polyflow, right? And all of this represents the detecting region, meaning that if you have an error inside this region that don't commute with Z, you will get detected by this detector, right? And so this is just a way to represent this. So at every time slice here, you are taking a cut at each time slice, and now you are trying to have it represented spatially. This is trying to give you a notion of the space of the detector at a given instant t. Does that make sense? It's actually hard to represent in 3D, so that's why we cannot use those type of plots, because you just need a lot of them, and you go up and down in time, and this allows you to see like to have a sense of the detecting region and where you are sensitive to which type of error.
Can you just say it? So when you're expanding it and contracting, are there 2 points in that cycle where you're measuring?
So yes, so the first, so this, sorry, you mean like the first initial point here? This is one cycle, and this is the expansion cycle, and then you have a second cycle, which is the contraction cycle.
At the end of the expansion cycle, you're measuring the
Yes, you are measuring the ancilla. So here you have a measurement here, and you have actually a measurement here. So a detector in the standard surface code spans 2 cycles. And this is a reminiscent of the first statement that for fault tolerance, you need to compare the 2 measurements that are next to each other in time, right? This is a formalization of this concept.
That seems like it's fault tolerant if there was an error that happened between the first cycle and second.
What do you mean? Yeah, here, if there is any error in this, you can catch it. You know it happened. And the idea is that now you tile them, and the tiling allows you to pinpoint where it happened. Okay, I may have missed the tiling, I'm sorry. But the notion is that depending how you construct those detecting regions, you can deform them a bit, and you can extract, like, you can maybe make simpler circuits or circuits that give you an edge in terms of hardware design. And so the first one that we look at is, instead of using the square lattice, we use like a honeycomb type lattice with just 3 neighbors per qubit. And those are like the comparison of the 2 detection slice, sorry. And this is like the slice of the 3-coupler one. And as you see, we don't use this direction, meaning that when we design the hardware, we can just completely forget about this one. We didn't do here, just for A/B purpose, but here are the results on the same grid on the same device as the one we show the standard execution of the surface code. And you see actually that the error rate is similar to what we get with the standard gate scheduling. And so we also reach a lambda above 2, slightly higher within error bar from the standard surface code. I'm an experimentalist, so I also care to understand this number. So we have started to do like a lot of benchmarks of the number of everything that is inside. And since those detecting region, this is what I was telling you, the detecting region are sensitive to the error inside that don't commute with the type of detecting regions that you have. So for instance, here you have a blue line in this case, and we have an X-like error in this data qubit. What this means is that this error will trigger the detector. And so now that we have all of those error mechanism benchmark from other experiments, we can actually reconstruct a full error model for those detector. And we can construct what we call like a model for the detection probability. So we call this like a stochastic poly-error budget. And there is like an analytical formula that is just the detection fraction with some log is just the sum over all the errors that are inside this detecting region and that don't commute with the detecting regions. So what is nice that this gives us an analytical model for all detectors that we can use to predict. So we can use to predict from component benchmark. And so here is the data. So this is for the 3-coupler. First, so those are like the weight 4 check in the bulk of the D5 standard surface code, and those are like the weight 2 on the boundary. And here you see a comparison between the model, so the model prediction from component benchmark and the experimental result, and you see a pretty good agreement that validates our model. So this we were pretty happy to have like a good agreement, because this means that we can trust our model and we can try to extrapolate to larger distance. So this is another visualization of this analytical budget, where here you see all of the detectors that we have measured and all of the contribution from each different type of contribution. What we see is that right now with our device, the CZ, or the 2-qubit gate, is one of our dominant factor. And the DD is also like a dominant factor. DD means dynamical decoupling, and this is just like the idle error during the measurement plus reset cycle. Okay, we also have been a bit deeper in like validating our model, and so those are edges. So if you look at the decoding graph, there is edges between each node, and those are like, we categorize them as T edge, between it's the same detector but like shift in time. We have S edge, which are just neighbor, and ST edges, which are a bit weird, but just detectors that are just like neighbor, but slightly moved in time. Here are me trying to animate those to be more explicit. It's not necessarily easy to see, but here you will see that the detector start from inside the other one. Here you see that they are just like neighbor, and here you will see that they are neighbor, but shifted in time. And once again, we can compare those with our stochastic model and validate our model, and you see that we have actually a pretty good agreement on all those type of edge from component benchmark, meaning that we can trust our component benchmark to start extrapolating to larger distance. So this is what we did, and we actually did the extra step of in our simulation, removing completely the force coupler and try to see which type of gain we can get, taking into account the TLS landscape. And those are the two curves, and what we are showing here is that if we are using an hexagonal grid with the current benchmark that we have, we could already gain a 15% increase on the lambda that we have. Meaning, if you think of this in other terms, this means that you can reduce the distance needed to reach like a certain logical error rate by a pretty large factor. Okay, is there any question on the tree coupler? Yes? Oh, sorry. Oh, TLS. Okay, so I'm sorry, I didn't introduce this properly. So in superconducting circuits, we have this issue where we have a two-level fluctuator. Those are just two-level systems that couple with our qubits, and they have like a very intermittent behavior, or like they will actually create poor performance gates. And so we have an optimization pattern around it, but of course, like we lose a bit due to this landscape of a fluctuator.
I guess the question is more like, what is that number? And is that something we extract from like microscopic measurement? Is there anything?
So we usually measure the density, right, experimentally, and then we just, so for those simulation, we have just generated, like I forgot the number, but we have generated several fake device that have a density similar, and like that have density and shape similar to what we observe experimentally.
Okay, so you pick the number and that doesn't change during the
Yeah, no, for this simulation, we didn't have time-dependent shift. Oh, yes? Yes. Yeah, so each color corresponds to a different gate. So the blue one is the CZ, so this is like the 31%. Orange one is DD, which is just idle during measurement error. And then red one, which is the next big one, is like the readout. What do you mean? The difference between the, so black is the experimental data, and the histogram is the model data from component benchmark. So what I was trying to say here is that we have actually a pretty good agreement and validation of this model from a component benchmark.
You can say that these are mostly random errors that influences TLS, or is there something more coherent errors?
I mean, for the CZ gate, we are mostly limited by coherence of our device, and the rest is like trade-off we have between speed versus accuracy of the gate. Those are mostly capture all of our error mechanism. Okay, so this was the first type of deformation, and this is actually a pretty dramatic change because it's allow you to remove, like completely change the connectivity, and this is like a pretty big deal in terms of experiment realization. The second one that I want to talk about today is the working surface code and leakage. Like, why would you care about a surface code that is working? Okay, so the data on the standard surface code that I showed at the beginning, we use the technique called data leakage removal. And this here, when we use it, we see this type of detection fractions that are really flat, meaning that errors are time independent in some sort. You always get the same type of error no matter at which time you are. But if you remove this technique, what you start to see is like rising of the detection probability with time. What this means is that you have an error that starts to accumulate over time and that create more and more logical error. And this is not necessarily a problem for small distance, because if you look at the logical error rate with and without this technique, you see that there is almost no impact for a small distance. And this makes sense because a distance tree is just sensible to one error. So as soon as you get one leakage, you get the error. So there is not much difference between having data leakage removal or not for small distance. But as soon as you go for larger distance, like the distance 5, you start to see pretty large gap between using or not using this leakage removal technique. And actually, if you look at the number for the lambda, you move from a 1.21, so barely above threshold, to something that is deep in the sub-threshold regime. Yes? Yeah, I'm going to this right after. So what is this technique and what does it do? So data leakage removal is the idea that if you have leakage on a data qubit, it's going to stay on your data qubit for almost forever, and it will start to accumulate and just create error in this way. So what data qubit leakage removal do, and I'm going to say DQLR from now on, what it does is that first you do like a leakage I swap, what we call a leakage I swap, which is just a swap of those two states. So if you have a 2 here, you have a 0 here, you are in a known state here, you are going to go into a 1-1 state here, and you are going to reset. So if you were starting from a leakage in 2 here, you will be in just an error on a data qubit that you will be like in the computational subspace and that you can correct for. This is the idea. It's transforming a non-computational error, which is leakage, into a computational error on your data qubit. And so this was, at the time, what was shown the impact of DQLR into the correlation between detection event versus the number of cycles. And you see that if you don't have any resets here, of course, you get really strong correlation between cycle at any time. As soon as you put reset here, you start to reduce a bit it, but you still have a pretty large correlation. And as soon as you had the DQLR, you really completely you diminish completely this type of error channel. So this is a key technology that has enabled us to reach those low performance. Yes? It can be higher, actually. And we had like there was a persistent problem where readouts will put at much higher state, we will have ionization of the readouts, which will be much higher. So actually, this reset is a bit more stronger than just removing the 2 states. But on the data qubit, we rarely see events above 2, just because the cycle is short. Oh, we want to do this every cycle, just so we actually get the right, like we can actually detect the error. We don't want long time accumulation at all. Those are like very bad for logical error performance. Okay, so like, sorry? So the leakage I swap is just like, you can think of it, it's like a swap between 2 on the data qubit, 0 on the measure qubits, into 1, 1 on those 2. So we are using a transition we are using this transition with our coupler between the 2 qubits to generate this swap. Oh, yes? Yeah, it's a CZ. It's a CZ gate. I have a slide on this right after, actually. So there was the question is that can we construct a QEC circuit that will actually take care of leakage without us having to use this extra gadget to remove leakage? And actually, yes, there is. And those are called like working circuits. And here is the idea, is that working circuits always swap data qubit and measurement qubit every other cycle. So for the first cycle, the measure qubit is going to get resetted. And as I said, this one will get rid of the leakage. And then for the next cycle, you are actually swapping the role of both. This can be done trivially with like some swap gates, but here we want to keep the qubit the qubit number constant as well as the number of cycles into this one. And this was indeed possible. So here is again the detection slice animation. If you look, you will see that we are changing the sublattice in the middle of the, And if you look closely, what happened is that we are oscillating between those two surface code, one which is here and one which is here. And if you look, we are really changing the two sublattice. So here I was on the diamond shape, and the diamond shape is now here, and we are now like the ancilla is becoming the square, the circle shape. So this, in principle, could help us reduce leakage without the help of decurer-like technique. So here is a dead slice, but no in a static frame. And actually, the only change of this compared to the standard surface code is that this, the direction of this layer is inverted. The C0 is just inverted direction compared to the standard surface code. This is the only difference. No, of course, the boundary of the code are a bit more messy, but it's another story. And we again did measurement of the lambda. So this is the reduction factor. We see a reduction factor of 1.7, which is lower than the previous implementation. But here we have completely removed the need for this extra gadget of data leakage removal. We can again do the error budget, and here we see a slightly less good agreement between prediction and measurement. So the reason why we think we have a bad agreement or like a less good agreement is because we think we have a complex dynamic of leakage into our system. And what we can do now is do what we call leakage slicing. So now at every time step, we just do a readout of the two states inside our code and on the two sublattice. So what we see is that when you do a reset on one sublattice, you eliminate the two population as you expect. And you see that like every other cycle, we remove leakage from one of the two sublattice. But what happened is that you can still have a bit of leakage that can transport from one sublattice to the other during one cycle, and this will still create a bit of correlation. So this is like time correlation for 3 experiments. The first one without DQLR on the standard surface code. The blue one is the standard implementation with the surface code, and the last one is with walking, but no DQLR. And what you see is that even though we reduce correlation at time scale, long time scale, we still have a discrepancy for just like t+2, which is this point here, and this we attribute them to just transport. So this is like the limit of this scheme. We want a way to reduce transport. But this, in principle, actually kill long-time correlation, but not enough just yet. So that's the limitation of this technique. So is there any question on this circuit? Yes? I mean, if you like, the performance of the standard with DQR is better, but it's just that you need an extra gadget, and that you need to calibrate it. You need to take it into account when you design the chip, and those are like a lot of overhead in fabrication and designing the chip. So this is why we want to look at this type of technique that can allow us to relax the constraint on designing the architecture. Does that make sense? No. This is an extra gate recalibrate. Okay, so, and finally, the last one, and the one that I think was the hardest experimentally and the funniest also, is the ISWAP surface code. So, now, the idea is once again to use like single detector. So, you can think of these gates, this CX swap gate, as a C0 followed by an I swap. And this is similar to an I swap gate, up to some single qubit gate. Why would you want to use this gate? So this is a gate that we are using for beyond classical experiments, and we know we can in principle do it with very high fidelity, much higher with the CZ. The second reason is that this gate has very, very low leakage. So we are hoping we don't need DQLR, and we can have a higher fidelity with this type of gate. This was the initial thought of why we would care about this. And as soon as you have this decomposition, you kind of imagine, oh, this is going to work. You are going to have the standard surface code, and you are going to have a bit of deformation due to the to the swap that comes right after. The shape that the surface code takes is absolutely not obvious, though, because now the detector at a measurement cycle don't look like a square. They now look like a arrowhead like this. And you actually oscillate in the bulk between arrowhead going in one direction versus going in the other direction. So once again, you have like the expansion cycle, and then you have like the contracting cycle. But no, like the shape are much more extremely deformed compared to the standard surface code. So here is a comparison with the standard surface code. So the beginning is kind of the same, but at some point you start to have those very large shape on the lattice that are showing the deformation. And actually what is kind of magic is that here the tiling of the surface code still work, and you still manage to tile a surface code even though you have this weird deformation going on. So we did, once again, implement memory experiment and measure the lambda for this one. This is our lowest lambda. And we get an error rate of 0.65%, but now like the component error model match very well, prediction match very well what we measure. We think the matching here is because we have almost no leakage with this specific gate. So why leakage will be less important with this gate? The reason is in the scheme we use inside the gate. So for the I-swap, we use an I-swap interaction, which is a 1-0 with a 0-1 interaction. So we put the 0-1 and a 1-0 on both qubits on resonance, and we let this interaction act. Whereas for the CZ, what happened is that we use an interaction between 2-0 and 1-1, and we do a full turn to do a C phase. This, if you calibrate it not super well, you will always have a leftover of 2 in this qubit. So this is why this can generate qubit, and this is something we know and why we need DQLR. But here you don't have this problem. The second benefit of using I-swap is that transport doesn't go up the ladder. So if you have a 2-state, you can never get a 3-state because your interaction is always between like 2, 0, 0, 2, or like 2, 1, 1, 2. You always stay at the same maximum number of photons in one of the two transmons. While for the CZ, if you have 2, 2, you can get a swap with 3, 1. So with CZ, you can get this nasty effect where you just go up the ladder of excitation in one transmon, which is extremely detrimental. And so here what we do is, once again, we do like a leakage slicing experiment, and we look at what happens when we start injecting leakage into this code. So if you do a CZ standard surface code, but you don't do DQLR, of course, the leakage shoot up and take a very long time to decay because there is no mechanism to remove it. If you use DQLR, it shoot up in the first time, like this is black, it shoot up in the first cycle, but then after one cycle, there is almost no leakage. And with the I-swap, you get rid of it actually fairly quickly, but not in one cycle. So what happens is in injection, there is still a bit of transport of leakage that appear, similar to the walking, and this is what creates this tail. However, the leakage generation is way lower than with CZ. And finally, like there is another question. As I said in the beginning, the I-swap is supposed to be our best fidelity gate. But what happened is that when we do beyond classical experiments, we actually take the C phase into the model of our gate, and then we compute the XCB fidelity using that gate, which is not a true I-swap. It's a I-swap plus some C phase. Sometimes we call it sycamore gate, or I-swap-like. You will see it that way. And we get a pretty large loss just to the fact that now the C phase makes this gate into a non-Clifford gate. And so now this C phase is actually an error channel compared to XCB. So now we have an extra entry here for this specific device that is actually almost at the same amplitude as data error during idling, during measurement of data qubit, or readout. So it's actually a really large error that we have here. And this is kind of the limitation of this implementation on this given device. Is just the trade-off between time of the gate versus C phase is not favorable. And this actually calls for having a device which will reduce this quantity. And the device that we use this experiment on didn't have this. Okay, and so with this, thank you for attention. So we have demonstrated 3 alternatives to the standard superscode implementation that show actually below threshold performance for all of those 3, but offer different trade-offs. And with this, if there is any question. Sorry.
Any questions?
So just on the previous slide, you were talking about how like your highest fidelity gate like is just this like ISWAP like rather than the true ISWAP. Could you imagine yet another deformed toric code where you used your ISWAP like gate rather than the ISWAP?
So that is actually so you want a non-stabilizer, like you want to non-stabilize your code.
It'll
that
be a
will be
non-stabilizer.
really good. Or like another way will be if there was a way to kind of like echo out the C phase through a cycle or multiple cycles. That will also be a way. I tried in Crumble. I didn't manage to get it to work. But there could be, it's not impossible that it's possible. It's just that nobody has it yet. Maybe I didn't say it, but like the ISWAP code is also like super exciting recently. Like someone found a way to use this delocalization of the ISWAP to put some LDPC flavor to it. Like those are like the directional code, and they use the ISWAP in a planar geometry to do some LDPC-like code, like the B-variant bicycle-like code. But the C phase, yeah, you want or a non-Clifford code, a non-stabilizer code, or you want to find a way to mitigate it, or at the hardware level, which I think this is what needs to happen. This was a device that was optimized for CZ, so it's completely different trade-off than for ISWAP.
Just to be clear, when you say non-stabilizer, do you mean non-Pauli stabilizer or like non-stabilizer at all?
Whichever work, I guess.
Thank you.
Any more questions?
Yeah, maybe I missed it. I think like I'm still a bit confused about this leakage removal, like, and if it's above 2 states. So is there a sense in which if you do this walking circuit, then you don't need to, then all of those are taken care of all at once?
So there
or
are.
like, is it?
So, okay, maybe I should go back to the slide. So DQLR is this pattern, right?
Yeah.
What happened is that if you have a leakage on the, let's say you have no transport at all. There is, transport don't exist. You have a leakage on your data qubit. This will stay forever, like as long as your two states survive. So it's going to stay T1 of your 2 states. And it's going to disrupt all of the adjacent qubits in a non-computer, like something that your code cannot take care of, right? So this is why this is bad. And now like the first gadget that we come with to solve it is to use this leakage, so this DQLR method. And the hope was that with working code, if you don't have any transport, this problem is fixed.
Okay, so maybe it's just like a technical confusion. So if you have measurement-induced ionization and you get above 2, then but that
this
doesn't
never
matter.
happen. Okay, this we make sure because of the first reset right after the measurement,
okay.
Get rid of that. And we don't have ionization really much like anywhere else than during measurement.
Okay, thanks.
Maybe I can ask one probably very basic question. With 3 coupler setting, can you show the figure again? I don't fully understand how you get the stabilizer by measuring the ancilla. I mean, it should work a certain way, but I guess I didn't get exactly how it's working.
So what happened is that so there is 2 flavors. Like the first flavor is that if you look, you are not, so the cycle extraction is like shifted every other cycle. So if you look, this guy is shifted compared to this guy. You will see on the lattice is shifted. So you are a bit moving. So the way it's done is that it's the stabilizer is here, and then it shifts a bit. Maybe it's better shown here. So if you look here,
Right.
because of the scheduling, you see like red become blue. What happened is that the blue is shifted here. So you shift a bit everything, and then with time reversal, we shift back.
Huh?
Does that make sense, or it's more confusing?
But I guess the summary is that with just this 3-coupler geometry, you can still get like ZZZZ by measuring the center ancilla.
Yeah, but you need to fold back the stabilizer with the C0. And it's just that we use this trick where like the last layer is just, instead of going one direction, it's going the other direction, but it has exactly the same effect. And we allow ourselves to move which measure qubit is going to be blue and which measure qubit is going to be red.
Okay.
Is the way you were explaining about why the leakage error happens in the CZ, and is it a problem of calibration or parameters drifting, things like that?
So even if you are like super precise, there is a lot of like external things that are gonna miss your, that are gonna change a bit the parameter and enough to create leakage. So indeed there will be like TLS entering and going out, but there could also be like different contexts in different moments of the cycle or things like that change from the context where you have calibrated them. So that there is a lot of like small variation that will be slightly off from the optimal point. And drift is actually also like a pretty large problem. And remember, like we will need to run those things for a very long time. So we need a solution. But I would say like even if you calibrate, we have never managed to calibrate so perfectly that there is absolutely no leakage.
Okay, let's thank the speaker.